Well, hello. Let's look at section 6.1. We're working on day 2, and we've got a few of the special events that happen when we're taking area between the curves. So let's get started. Here we go. Let's look at, we've got an f of x function that is cubic. We've got a g of x function that is quadratic. So I think you can pick out which is which. So I'm going to try and highlight my cubic. And I'm going to name that f of x. And I'm going to go over here and name it again. Then I'm moving into my g of x, the blue curve, as I'm calling it, and I'd have g of x curve there. I'm also going to write g of x right there. You can see that clearly we have two defined regions. And what do we want to do with these regions? Well, I want to highlight them. So I've got this green region. And then if you have something of color or just different pattern shading on this, we do have two clearly distinct regions. I'm going to name this one region R and this one over here region S. And when I look at region R, I notice that the f of x curve, the red curve, is over top the blue curve. But when I switch over to S, I have the reverse scenario. I have G over F. So I'm going to need to use two integrals to capture the area and add them together. So what it asks us to do is to define these points of intersection. And we know we can accomplish that by going into each of these functions and setting them equal to one another. It's cubic, which makes it a little bit more difficult, but this one actually turns out pretty nice. If we add x squared to both sides, the x squared term disappears, doesn't it? It zeroes out on us. And then I would subtract 2 and get 3x squared minus 12x equals 0. Okay, whoops, I should have cubes there. Sorry. Cube and cube. Let's GCF a 3x out of this, and I should expect 3 solutions, and indeed I'm seeing 3 solutions, -2. And that's going to correspond with this value being -2, that being at 0, and this one having an x value of, where are we going to squeeze that, of 2. That's going to help me when I write my integrals. So I'm going to erase this piece because I want to move, see if I can move this up. Let's write the integrals and solve them. So I'm going to do them separately so you can see. Let's write this first one in red for region R. Region R will be the integral from -2 over to 0. These are x values. So our functions should be written in terms of x. And I want the top function minus the bottom function. And in this case, I'm going to have -2 to 0. My top function was that cubic, so I'm going to have 3x cubed minus x squared minus 10x. And the bottom function was the blue function, the 2x minus x squared quadratic function, dx. And I know that you could solve that by hand, but I'm going to give us the area on that. That is 12. Now let's go after S. So we've got the region R defined. We've got it all solved. We'll just say this was calculator active. Let's go after region S. Let's use blue ink since we wrote it in blue for S over here. S is equal to the integral left bound to right bound, 0 to 2. Top function was g of x in this case, so I want to put g of x, 2x minus x squared, take away. Bottom function is our red one, the cubic function. And that will give us the length of a rectangle that sits between g of x and f of x. And if I take g minus f, that'll give me the length. I multiply it by the width, that is dx. So imagine this thing having a little bit of width. very, very small width. And if I calculate out this using a calculator, I get 12 for that one as well. So I get the total area is equal to 12 plus 12, or 24 square units. So if I have a shift in those functions, what was once top function becomes bottom function, you will want to do those in separate integrations. All right, the next one gets into what happens if I have a function, and I want to color this, that switches between top and bottom, black over this blue. And then we had the linear function, and you can see how the linear function is not on top of the blue function. Well, yeah, on top of the blue function the entire time. You know what? I drew that a little funky. Let me back up. I want to do that over again now that I'm looking at it. Let's do purple all the way to there. And then I have blue. So let's relook at this. Green function is definitely over the blue function when I'm right there. But as I move to the right of this dotted line, you can see it becomes purple over purple. So I can't just use one integral and have the green be the top function over what would have been the blue function, which was the quadratic, right? The blue bottom function, because blue does not stay bottom over the entire region. We have this area where we have purple going on, and we've got to address that. So if I were to do with respect to x is what that means, then I would need two regions. I'd have to have a region R on the left and a region S on the right, and calculate it in 2 steps. A little bit of work. Instead, there's a technique that we can come at it and look at it with respect to y. And when I do that, I'm talking about like horizontal rectangles. Think about like flooring. If I were to lay wood flooring, I've got choices, right? I can lay the planks horizontally, or I can lay the planks vertically. How would I capture the length of those planks? Well, down on the second example, it's easier to do because this green function is always situated to the right of my black function. So in this case, it would be green function, which is on the right, black function, which is always on the left, and I can call it right minus left. If I start doing right minus left, then I have to be in terms of y. Okay, so that's why we're saying with respect to y. So y becomes the input, x becomes the output. Well, this is the x-axis, right? And if it's the x-axis, then the distance of that segment would be like an x2 minus an x1 value, giving me the total change in x. Just like here, we had a y2 over a y1, and the difference between those became a change of y. So this will be easy. I just need to capture those two intersection points. And those intersection points could be found by setting things equal. I know that I'm just going to go ahead and drop in, get rid of a little bit of this work here. Drop in this point here is the point -1, -2. This point here is 2, 1. And we certainly could have set these two equal, found the y values that are in common. All right, we have this. Now let's go with which is our function to the right. It's the quadratic. Notice how this is written into an x equals 3 minus y squared. That's because we want y to be acting kind of as the independent variable in this one. And this linear function is written as x equals y plus 1. So now the area formula, when you're with respect to y, will be some y value, I'm going to call it c, to some y value d. Then I'm going to do the right function, or the right curve minus the left curve. The thickness of our rectangle, remember, is a dy thickness. So let's go ahead and walk this one through. Our area will be the integral. I need y value to y value, smallest to largest. I need right function, 3 minus y squared, take away left function, y plus 1, multiplied by the thickness, dy. And we could go ahead and solve that. It would end up being a 4.5. I used the calculator and got that. Okay, just a little bit different approach. And easier because this clearly, the quadratic was clearly to the right of the linear function for the entire interval from negative 2 y value up to positive 1 y value. Now, I think I'm going to not do the horizontal method and do it on the next one. So, if the upper curve requires 2 or more equations, then using a right curve and a left curve may make things easier. I think I missed a letter in there. There we go. So if we had something like this, we can clearly see that there's a region, if I were using top-bottom, actually it'd sweep all the way around to there, wouldn't it? Where the same curve is on top of itself. And I'd have to break that curve into 2 functions if I were to use x values. So I'd have this breaking point here. Oops, there we go. I'd have that breaking point where I'd have 2 regions if I were to work in x values. But if I work in y values, so much easier. Then I have blue curve minus red curve. And let's just rewrite this equation in here. The area is equal to c to d, that c value being the height, and the d value being the height of those y values. So these are in y's, and then I want my f curve minus my g curve. And these are going to be in terms of y, so f of y minus g of y dy. Okay. Left, I'm sorry, that's not correct. Right curve, left curve. Y value, y bounds. This here, of course, is our width. So we have that horizontally placed rectangle with the dy thickness, and this would be like a y2 minus a y1. I'm sorry, I should say x, shouldn't I? In terms of y, the function will be in terms of y, but the output would be in terms of x, so that we get along here how much x difference there is. All right. Let's look at this problem. Determine the area of the region. I think I skipped number 6. I think I double clicked. Okay. Let R be the region in the first quadrant bounded by the curves y equals natural log y equals 5 minus x and the x-axis as shown. Find the points of intersection of the two curves. This would definitely be calculator active so that we can capture this one. So all I would do is go natural log of, I'd probably put that in my y1 equation, y2 equation. I would go 5 minus x, and then I'm going to look to see where y1 and y2 intersect. And the intersection is 3.69344. That should be plenty of decimal places so that we can get accuracy out to 3 decimals as required by the AP. Next, it says write an integral expression in terms of x that would give us the region R. If I were to write it in terms of x, I would need two functions. So let's split right there. And we know that this is y equals natural log x. And we know this is y equals 5 minus x. So let's call this region S and this region, let's just do T. So we broke it into two separate ones. Shade it up if you wish, so it even becomes more clear. So I've got region S on the left, and I've got region T on the right. Write an integral expression in terms of x. So I would have region S equals the integral from 1 to this point here is 3.69344. That x value that we captured from the calculator. And I want top function minus bottom function. Natural log x, and then we were bounded by the x-axis, which is a y equals 0 function, correct? I could say minus 0. I really don't have to, but since I was talking about top minus bottom, I thought you might want to know, well, what would you use for a bottom function? And then I would have dx. That value, I'm not sure I have it. I did not calculate that separately. And then t is going to pick up at 3.69344. And it'll run to, well, if x is 5, that'll give us 0, so it must run to 5. Top function, linear function, 5 minus x. Bottom function is 0. And that would give us t. And then for total area, I just need to sum s plus t. Let's take another approach. Let's do the integration with respect to y. So now I have right function, left function, and I want to situate the rectangle horizontally. Up here we had rectangle, we had rectangles situated vertically. Width of dx, this one, width of dy, which really expresses to you how you're going to set your integral up. All right, so we are going to integrate one big region R, and that's going to be from 0 to that height, and I got to go back up here, which was 1.306559. That's that y value. So my integral is going to run from 0 to 1.306559. I'm going to take the right function minus the left function. Right minus left. dy. Oh, but my functions are expressed, weren't they expressed as x's? Yeah, this was y equals 5 minus x. That will not work for this. So we've got to transfer our equations. Where's a good spot to do that? Maybe right underneath here. So I have y equals 5 minus x. Let's solve for x. That'll end up being x equals, add x, subtract y, 5 minus y. There is, let's scratch that out. Let's rewrite this, because that's the one we want to use. All right, so r is going to equal 0 to 1.306559. Left or right function, 5 minus y. Subtract left function. This was natural log y equals natural log of x, if I remember correctly. So I have y equals natural log x. Solve for x. Then that's going to look like, looks like we have to take e to both sides, right? So I will have the function, let's scratch out this and write it in terms of y. So x equals e to the y now. Okay, over here, that's my left function, e to the y, and then multiplied by thickness, dy. And then it says to calculate the area of the region. It might be fun to calculate both of them and make sure, but region R comes out to be 2.986. Remember, we always need 3 decimals of accuracy for AP. All right, that took some time, and I'm going to allow you to work with number 7 on your own. The answer should turn out to be 4.5. You know, they gave you a little bit of a gift on this one. It's already solved for y's. So what you need to do is work on transferring this into an x equals as well, so that we can do the integral of the right curve minus the left curve. And work in terms of dy. So you'll need a y equals and a y equals bound. You need to find this and this. Looks like they might be pretty obvious, but just make sure they work. Plug those y values back into your function. Make sure that they come out to where you think they are, and you should be good. And then I don't think we're going to do this today. That would be review, so I'm going to pass on that just to get you guys done. And there will be a Delta Math assignment for this particular unit. Thank you.